Hello, we're here in Beijing, China, and my name is Alan Teyoton. We are going to be speaking about a topic today that should be a really simple topic for any aerospace engineering student, but it's also a really complex topic to explain because the mathematics behind it still seem pretty fuzzy. They are still in development, and it's something that we need to still research a lot about. So, we're going to be explaining how airplanes fly. And to understand how a plane flies, we need to first take a moment to make a small mental experiment. We need to picture the aircraft as a metal tube. Like, let's imagine a metal tube, like round metal tube that is immersed in a water tank. Let's picture this imaginary metal tube. If it would just stay still, motionless, it would sink to the bottom to the bottom of this water tank due to its weight. However, if the metal tube was suddenly capable of rapidly moving forward through the fluid that surrounds it, water in this specific scenario, a combination of the movement and a slight tilt upwards would cause our imaginary metal tube to start rising within the water tank. Well, this is exactly how we should picture an airplane, like a tube made out of a specific material, surrounded by a fluid that is capable of a forward movement so fast that it causes it to rise through the fluid that contains it. In the aircraft's case, this fluid would be air. Nevertheless, it is important to mention that the plane has a couple of added factors contributing to its capacity to rise through the air. One of them is called an airfoil. An airfoil is basically the shape that a wing is designed by. So put it in simpler words, it's the shape of an aircraft's wings. An aircraft will be incapable of flight without this added characteristic, as we know that an airplane weighs a significant amount, and its composition is far more dense than the air's. Even though today we constantly have new discoveries and new developments in science that make for new, more efficient materials, less dense, lighter materials, like, for example, fiberglass. The materials that airplanes are made from are still far more dense than air, and they still weigh a lot. So, an airplane should have and has specially designed wings called airfoils that move the air on the top of the wing faster than the air below the wing, creating higher pressure under the wing. Energy flows from higher to lower energy levels, and the pressure difference above and below the wing causes the upward force called lift. So if this airfoil was not present, control over the aircraft's flight path would be non-existent. The other factor that we need to add is the engine, which creates the thrust necessary for the airfoil and the plane to move forward, traversing the fluid. Airplanes can fly due to the careful maneuvering and control of the four main balancing forces present around the aircraft. These four main forces are called lift, which goes up, weight, which goes down, drag, which goes backwards, and thrust, which goes forward. Thrust pushes the plane forward through the air. Drag opposes the thrust force as it creates friction with the air that surrounds the aircraft. The weight pushes the aircraft down, and the lift counteracts the weight in order to get the airplane flying. Humankind's desire to fly started early in modern civilizations. The dream of being able to soar through the skies like a bird was nothing short of fantasy. Myths and legends originated from the inexorable wish of conquering the skies. From ancient Greece's Daedalus and Icarus, who made wings from feathers and wax and attached them to their bodies to escape from a cruel imprisonment they were subjected to Persia's King Kashkaoush, whose throne was attached to eagles for it to be able to fly. But besides that, some exceptional individuals throughout history took the first steps towards making this, at that point, impossible dream a reality. So, Chinese people were actually the creators of the very first flying-oriented invention, which was the kite, or Fengzhou, as it was originally called. Leonardo da Vinci was the first person on record to have actually studied the science of flight. Modern day helicopters are loosely based on his design called the ornithopter, which we can see over there. The ornithopter was the first real study of flight that is on record today. We can see some first drafts of an ornithopter. We can see that it looks kind of like a helicopter. Well, however, it was not until the 1900s, exactly the year 1900, that Orville and Wilbur Wright decided to take a real step toward making humankind fly for real. This time, they studied from earlier aviation pioneers and experiments. They obtained all the knowledge available to them during their time, during their era, and using only a wind tunnel, a kite, and a 12 horsepower engine, they succeeded at piloting the first manned heavier than air flight, which lasted for 12 seconds and traveled at a 120-foot distance. This was also one of the first times someone studied air behavior on airports, which takes us to our main topic. How do airplanes fly? Well, as we already mentioned, they fly due to a careful maneuvering of balancing forces and the shape of an aircraft's airfoil. You can see the four balancing forces here: the lift that goes up, the weight that goes down, the thrust that goes forward, and the drag that goes back. Well, at that moment they were not quite sure how the airplanes fly, because they were doing this basically in just trial and error. So they were able to fly it, but they didn't really understand how it was capable to do that. They didn't know how it flew. So this is basically due to the different airfoils creating different results when interacting with it. Today, we can explain what happens as the difference of pressure between the lower and the upper part of an airfoil surface. Simply put, the air particles that pass through a longer convex surface take more time to come into contact with their counterparts that slide through a shorter and more straight path, a more flat path. This causes a pressure difference, and adding the thrust provided by the engines, this creates the desired effect for an airplane to be able to fly. We can explain this phenomenon with Bernoulli's principle, which states, we can see here, as we already mentioned, we have the weight, which is inherent to any body that has mass in a planet. Then we have the lift, which counteracts the weight. We can see how the four main forces act on an aircraft. And, well, going back to Bernoulli's principle, you can define it as pressure 1 plus 1/2 of pressure times velocity squared. 1 plus pressure times gravity times height equals pressure T. Here, to understand how Bernoulli's principle applies mathematically to the lift, we can look at this equation. So it's written as I already mentioned. And in the context of light, this equation can be simplified as the changes in height for air moving over a wing or a minimum. So this allows us to focus primarily on the pressure P and velocity V of the airflow. According to Bernoulli's principle, if the air velocity over the top of the wing is higher than the air beneath the wing, then the pressure on the wing's top surface must be lower than the pressure on the bottom surface. This pressure difference creates an upward force in the wing known as lift. So here we can see how traversing through the convex part on the top of the airflow takes a longer time to arrive at the rear of the airflow, while the particles that flow through this smooth, flat surface take a short time to arrive at the rear part of the airflow, causing the force of lift. So we also have to talk about Newton's third law. We actually have four forces that interact with the airflow and they cause the airplane to fly. Well, this is exactly because Newton's third law implies that whenever there's an action, for every action there is an equal and opposite reaction. So for the force of lift, we have an opposite force of weight. And for the force of thrust, they have an opposite force of drag. So basically what Newton's third law says, simply put in simple words, it says when a person pushes a box, the box pushes back equally. So whenever I push a wall, even though the wall does not move, the wall is pushing me backwards. And that is actually what's causing the wall not to move. So this law describes the mutual forces that two bodies exert on each other. And it is foundational in understanding the behavior of objects in motion, and plays a critical role in explaining how airplanes generate lift, particularly in conjunction with Bernoulli's principle. In the context of flight, Newton's third law helps explain the generation of lift and thrust. When an airplane wing moves through the air, it exerts a force downward on the air particles, and this is the action force. The wing pushes air downwards and backward. According to Newton's third law, the reaction to this force is the air pushing back up against the wing with an equal force in the opposite direction. This reaction force contributes to the lift that supports the airplane against the pull of gravity. To better understand this, let's look at the wing's shape and motion. The airfoil, or wing, is angled slightly upward, allowing it to direct the air downwards as it moves forward. This angle is known as the angle of attack. It is carefully designed to maximize lift by redirecting the air. The air moving below the wing is compressed and directed downward, increasing the air pressure beneath the wing. The downward deflection of air creates an upward lift on the wing due to Newton's third law. As the air is pushed down, it reacts by pushing the wing up. If the angle of attack were to surpass the adequate angle, the plane would follow, as it would cause the air to push the airplane downwards, causing it to lose control. This principle also applies to an airplane's engines. The engines create thrust by expelling exhaust gases backward at high speed. So, to go further in depth into Newton's third law of motion, we can see the equation here, which simply put, is the force equals a change of momentum with a change of time. So, well, the difference form or the expanded form will be the force is equal to mass 1 times velocity 1 minus mass 0 times velocity 0 divided by time 1 minus time 0, which in time is mass 1 stands for the final mass, velocity 1 stands for the final velocity, minus mass 0, which stands for the initial mass, velocity 0, which stands for the initial velocity, time 1, which stands for the final time, minus time 0, which stands for the initial time. In this case, we can simplify the equation since we know for sure that our airplane is not going to suddenly change in mass. Its mass is always going to be the same. So we can use the equation with a constant mass. So the force will be equal to the mass times division of the final velocity minus initial velocity divided by the final time minus the initial time, which can further be simplified into the force being equal to the mass times the acceleration. And we also need to know that velocity, acceleration, momentum, and force are vector quantities, which can be multiplied and divided by each other. So, how engines create thrust? As we were saying, they pull air in and fuel, and they just expose this air and fuel back. So this backward expulsion of gases generates an equal and opposite reaction that propels the airplane forward. The faster the gases are expelled, the greater the forward thrust produced. So applying Newton's third law of motion enables the airplane to reach the speeds necessary to generate sufficient lift for takeoff. The combination of Bernoulli's principle and Newton's third law of motion allows the aircraft to achieve both lift and forward motion. While Bernoulli's principle explains the pressure difference that produces lift across the wing surfaces, Newton's third law provides insight into how the wing's angle and motion generate the reactive forces that complement this lift. These laws create a balanced force system that allows the airplane to rise, stay in the air, and move forward. So, how do the engines create this thrust? This can be explained by the 4 steps that we are going to show here. An engine creates thrust by accelerating air, which we can see here, entering the engine, or excess gases that are put inside the engine in one direction to produce an equal and opposite reaction force that propels the aircraft forward. So they expose the gases backward. So how do engines create thrust? They create this thrust by taking air inwards and accelerating this air or the exhaust gases that are put in them in one direction to produce an equal and opposite reaction force that propels the aircraft forward. According to Newton's third law of motion, in jet engines, for instance, this process is accomplished through a series of steps involving air intake, compression, combustion, and exhaust. You can see here that the air is pulled inward and through the intake by this fan, and then it is exposed in the rear part backward, so it creates an opposite reaction of moving the airplane forward. So we can break down how an engine creates thrust by analyzing these 4 stages. So air intake, as we were saying, the engine first takes in a large amount of air through an intake at the front of the engine, which we can appreciate here. In a jet engine, this air is drawn in and compressed by rotating fan blades, allowing a substantial volume of air to enter at a high speed. We have the fan blades over here. Then, compression. After intake, the air is directed into a compressor, which we can see here. These pistons compress air. It's a series of rotating blades that increase the pressure of the air. This compression increases the density of the air, making it more effective for combustion. Then we have combustion. The high pressure air then enters the combustion chamber, where fuel, that is typically kerosene, is injected and ignited. The fuel-air mixture burns at extremely high temperatures, causing the gases to expand rapidly. This creates a high-pressure, high-temperature flow of exhaust gases. Then we have the last part, the exhaust part. The hot expanding gases are forced through a narrow nozzle at the rear of the engine, accelerating the gases as they exit. The high-speed ejection of gases in one direction creates an equal and opposite reaction, pushing the engine and the airplane inherently forward. This reaction force is what we call thrust. So, different types of engines generate thrust. We have, for example, the turbofan engines. Turbofan engines commonly used in commercial airplanes. These are the most commonly used engines. Turbofans combine a fan, which we can see here, with a jet engine. The fan at the front helps pull in and accelerate a large volume of air, producing additional thrust by pushing some of the air around the core of the engine. You can see here, the core here takes some of the air, and around it we have a couple of pathways that also take in some air. This bypass here creates a quieter and more efficient thrust, making turbofans ideal for passenger aircraft. Then we have also turbojet engines. These engines are designed to generate maximum thrust at high speeds, often used in military or supersonic aircraft. Turbojets compress and combust air entirely through the core engine without bypassing air around it, which generates a very high speed exhaust. This is high speed exhaust with also really loud noise. So they are not highly efficient in commercial flights because they create a lot of noise, they create a lot of heat, and well, they waste a lot of fuel. But they create a really, really high speed exhaust of gases. We can see how every single particle of air that goes into the engine here is processed and is compressed in these in the combustion chambers. So they have, as we can see here, this engine specifically has two combustion chambers, and they are designed to create the highest speed of exhaust gases possible. So then we have turboprop engines, which are used in smaller aircraft. They are composed of a prop, a gearbox, a compressor, a shaft, a combustion chamber, as you should have, a turbine, and an exhaust. These engines power a propeller using a gas turbine engine. The turbine rotates a shaft, we can see here, connected to a propeller, generating the thrust by moving large volumes of air back. Turboprops are highly efficient at lower speeds and are commonly used in regional and smaller aircraft, as we just mentioned. So, each of these engines relies on the fundamental process of accelerating air or gases to create thrust. The thrust produced depends on the speed and mass of the expelled gases. The faster and more massive the gas is expelled, the greater the thrust generated. This thrust pushes the airplane forward, as we already mentioned, allowing it to reach speeds necessary for generating lift and sustained flight. we're going to go more in depth into the turbofan engine, as it is the most commonly used. This is an advanced type of jet engine, widely used in commercial, sometimes military aviation, due to its balance between efficiency, thrust, and noise reduction. It combines features of both the jet engines, the turbojets, and propellers, using a large fan to move a high volume of air. This design creates thrust by expelling two streams, as we already mentioned, of air. One through the core, that goes through a combustion process, and one around the engine. And we already mentioned it has two other pathways around it, resulting in a high efficiency engine, ideal for long range and high speed factor. So it has the main path and it has the bypass path. So the key components of a turbofan engine are, as its name implies, the fan, and this is the first stage and the largest component in a turbofan engine, with large blades that pull in and accelerate a significant amount of air. This air is then split into two streams, or two pathways. As we already said, this is the main pathway inside the engine. Then we have the two outside pathways, the bypass pathways. So the bypass air is the portion of the air that bypasses the engine core and is expelled directly through the rear, creating additional thrust without any combustion. As we already said, it goes through. And then we have the core air. The remaining portion of the air enters the engine core for compression, combustion, and exhaust. Then we have the compressor here, what we can see here. The core air then enters the compressor, where a series of rotating and stationary blades compress it to increase its pressure significantly. Often it is compressed up to 10 or even 30 times the intake pressure. Compressing the air raises its density and temperature, preparing it for efficient combustion and making it more easy to combust. Then we have the combustion chamber, where here's the first red part, as we can see here, is where air is heated, to put it in simple words. So the compressed air is then mixed with fuel and ignited in the combustion chamber. This combustion process rapidly increases the temperature and pressure of the air-fuel mixture, generating expanding gases that flow towards the turbine. And we have, naturally, the turbine. The turbine extracts energy from the high-pressure exhaust gases to drive the compressor and the fan. The turbine is composed of rotating blades that are driven by the exhaust gases, allowing the turbine to convert thermal and kinetic energy into rotational energy. Then, at the end of it, we have the exhaust nozzle. The remaining hot gases pass through the exhaust nozzle, where they are accelerated out the rear part of the engine. This expulsion of gases creates the core thrust, while the bypass air also exits to produce additional thrust. So, this is how a turbofan engine works. And mathematically, we can see here that this is a general equation for thrust produced by a turbofan engine, in which the mass flow rate stands for the mass between the air and the fuel that is put inside the engine. Then we have the exit velocity, so we have to multiply the mass times the exit velocity of the air minus the entrance velocity of the air to obtain the force of thrust created by a turbofan engine. So, the combination of the thrust created by an engine and the lift that is created by the airfoil are the two main factors that create the desired effect for an airplane to be able to fly. So, this is how an airplane flies. It's a brief explanation. I hope it's understandable. I hope you guys enjoyed it. And, well, thank you so much. Have a good day. Thank you for watching. Goodbye.